All right, this video will continue talking about SN2 reactions. So just going back to, as a refresher, SN2 reactions are substitution. The leaving group leaves a molecule, it is substituted for a nucleophile. And you have the mechanism here with an example. We talked about transition states and reaction coordinate diagrams. And that not all substitution reactions will happen at the same rate. We had discussed these two factors, leaving group ability and structure of the nucleophile, in class. So this video, we're going to talk about structure of the electrophile to start off. And one thing I want to note is the term alpha carbon is going to come up when we're looking at an SN2 or even any substitution reaction that has similar reagents. The alpha carbon is the carbon where the reaction happens. So alpha, Greek letter alpha, that's the alpha carbon. And then a beta carbon would be any carbon bonded to that one. So this is a beta carbon and this is a beta carbon. Those terms are going to come up in this lecture and in the future. So I just want to make sure that is clear. The alpha carbon is the one that participates in the reaction. And then the beta carbons are bonded to the alpha carbon. Okay, so continuing to talk about structure of the electrophile, just scrolling down to where we'll start that. And we're starting with this table of relative reaction rates. This is for substitution reactions. And we're looking at a reaction. This is in the book, by the way, so you're welcome to also look at it there in the text that is along with it. We're talking about iodine as the nucleophile. Br is the leaving group, and this R group is what we're talking about. That's what's going to change. So for example, if it's CH3, if R is CH3, I'll draw this one out. So it's bonded to a bromine and 3 hydrogens. Okay, so that R is a CH3. We're calling that, of course, a methyl. The relative rate of this SN2 reactions is 145 molarity per second. If you change the alkyl substitution on a beta carbon, so now we have to introduce a beta carbon. Let's make it, here we have a beta carbon. All right, this is the alpha. This is beta. And instead of a methyl group overall, we have a propyl group. So we have a CH2 CH3. That decreases the reaction rate quite a bit. We've got this 0.82 as compared to the 1.45 just by adding a beta carbon and one more bonded to it. The addition of this group here, the CH3 and the CH2, really both of these compared to the methyl, hinders the ability of the nucleophile, so that was I- in this case, but you could apply it to other nucleophiles, to be able to come in and create a bond. Remember, single bonds are always rotating, so this larger substituent, the propyl group instead of a methyl, slows down the reaction rate. The rest of the table shows other substituents, other electrophile molecules, so like isobutyl here, that decreases the rate even further. If you have this is neopentyl, we can talk about what that is. This is 5 carbons. So we have the beta carbon bonded to 3 additional carbons. So greater number of branching carbons, that slows down the rate quite a bit. But this is all with the CH2 as the alpha carbon, right? That carbon is still bonded to 2 hydrogens. If you add substitution to additional hydrogens there on the alpha carbon, that decreases the rate even further. Like if we were to make this one a CH3 as well, that would be even slower and it decreases quite a bit. So as a little summary here, we can say substituents on the electrophilic carbon matter. So a greater number of substituents that are not hydrogen. Or we can say more branching. So instead of a linear molecule, there's branching. This slows the reaction rate. And we'll say substituents, I'll abbreviate here, hinder nucleophiles ability to collide with the electrophilic carbon. Okay, for a reaction to happen, the two reagents have to actually collide with each other, like physically collide with each other. And so the iodine in this case has to collide with that alpha carbon. But if there are more substituents and more branching on the alpha carbon, it will be harder for the iodine to reach that carbon. That makes the reaction happen slower. Here's a visual of looking at bromide reacting with methyl iodide compared to 2,3-dimethyl propyl iodide. So reaction A, we have Br- as the nucleophile right here, and CH3I methyl iodide or 1-iodomethane, another way to name it, right here. So this methyl, there's a carbon and 3 hydrogens. The bromine's able to come in and bond, and the iodine can leave. If we use this space-filling model, this better represents how electron clouds, the space that electron clouds occupy. And so there's more room on a side of that carbon that the iodine is not on, and then the iodine can leave. Now, if we compare this to 2,3-dimethyl propyl iodide, we have this structure down here. This is actually 2,2, not 2,3. Little typo there. So the alpha carbon is a CH2, but this beta carbon now has 3 additional hydrogens or CH3 groups bonded to it. This hinders the bromide's ability to come in and bond to this alpha carbon. So there are van der Waals repulsions because where the bromine needs to come in to bond to this carbon that's bonded to iodine, it's repelled by the other atoms, those branching atoms. If you look at the space-filling model, you can see there's a lot less room for that bromine to come in, and the iodine still has to leave. So again, that just slows down the reaction. We can call this steric hindrance. We've used that word before. when we talked about conformational isomers. All right, less room for the reaction to proceed, or for that iodine to come up. When the substitution of the alpha carbon starts to increase, the reaction actually doesn't proceed through an SN2 reaction. It'll be an SN1. So we're going to learn about SN1 here. Unimolecular nucleophilic substitution. So very similar to SN2, but this one here means unimolecular. That means the rate depends only on one molecule. We'll identify what that molecule is when we write out the mechanism. Okay, let's do general reaction scheme. We still have a nucleophile, we still have an electrophile, but our electrophile has greater substitution at the alpha carbon. So let's draw, we'll do similar to SN2. We have nucleophile, this will be our electrophile, and we'll say it's bonded to R1, R2, and a leaving group. So far it looks the same as SN2. But these R groups are usually more substituted. This alpha carbon is more substituted. So the nucleophile, if you imagine these R groups all being larger, right, the nucleophile struggles to come in. So actually what's observed is that the leaving group leaves first. So that's the first step, is just the leaving group leaving. So we still have the nucleophile. Now we've generated what we'll call a carbocation. So although the three R groups are still bonded, we now have a positively charged carbon, and then the leaving group has left, so we'll give it electrons and a negative charge. Okay, let's add some notes here. I'll use just pink for the first step. So first step of an SN1 reaction is carbocation formation. So carbo for carbon, and then cation for it being positive in the second step. We often abbreviate this as C+. Next, now that we've generated this carbocation and we've removed that leaving group, these R groups have more room to kind of rearrange. The nucleophile has an easier time to come in and bond to that carbocation. So that is step 2. That will produce the product. And because everything doesn't happen in one step, we don't observe the same sort of inversion of, because everything happens in one step, we don't observe the same sort of inversion of stereochemistry. We actually, in SN1, we observe both stereoisomers. So you would see both nucleophile bonding on the left, and we'll draw out why this is shortly, and nucleophile bonding on the right. So that's one big difference between SN2 and SN1. When you're thinking about products specifically, SN1, you observe both configurations. SN2 is just one configuration. Okay, let's go back to the mechanism. So we said first step is carbocation formation. In the second step, we formed this carbocation. So let's talk about this a little bit. This carbocation intermediate. By the way, this term, intermediate, this is an observed molecule, so it's not a transition state. It is observed for a period of time, but it is not the final product. It continues to react. So that's what our intermediate is. Now, if we were in class, I would ask everybody, what's the hybridization or the molecular shape of the carbocation? Thinking back to Unit 1. Well, this carbocation has 3 electron pair domains. That means it has sp2 hybridization. All 3 electron pair domains are bonds, so it's trigonal planar. So this is a planar molecule. R1, R2, R3, and the carbon are all on the same plane. I'll try to draw this kind of viewing from the side. So if we put our, let's say R1, R2 is pointing behind, R3 is coming forward. These are all in the same plane. So this would be a flat molecule. If you use your sp2 parts of the model kit, this is just trying to show shading in that plane. All of these are in the same plane. If you use your model kit and you make a trigonal planar geometry, you'll see that they are all planar. So because this is planar, that means there's equal room above, in the way that I've drawn it here, on one side of the carbocation above or below for the nucleophile to bond. So this nucleophile can bond on top or can bond below, just based on the way I've drawn it here. The result is both stereo centers, both configurations observed. Second step, just to add a little bit more detail, is when the nucleophile bonds to the carbocation. Okay, so we have 2 mechanism steps. First is leaving group leaving, forming the carbocation. This is a high energy intermediate. It is very reactive. This second step is very quick because we formed an open shell carbon. It is going to react very quickly with the negative or electrons that are available from the nucleophile. This first step we will call the rate determining step. Because this is the slower of the 2 steps, forming the carbocation. So the rate is dependent on how fast this step occurs. This step only includes the reaction of 1 molecule. Now this is how we get unimolecular. This is why it's SN1. So the rate of SN1 reaction, I don't remember if I had space here. I don't. Okay. So the rate is equal to K, that rate constant, times the concentration of the electrophile. The rate only depends on the electrophile. That's why we call it SN1. So that's a difference between SN2 and SN1. Okay, let's draw the transition states. When we first talked about transition states, we discussed how each reaction step would have its own transition state. So if we start with step 1, and how about we number these? So this is step 1, and this is step 2. So transition state 1, we'll draw that first. Remember brackets to indicate it is hypothetical. This is the change in the electrophile from starting material to the intermediate. So the carbon to R group bonds don't change. But the carbon to leaving group bond does change. So that one breaks, that will be a partial bond. The leaving group started off as neutral right here and then became negative. So in the transition state of step 1, it has a partial negative charge. And then carbon started off neutral and then became positive. So in the transition state, it has a partial positive charge. So that is this transition state for step 1. Transition state for step 2. Now we're showing the formation of the nucleophile bonding to the carbocation. So the nucleophile is involved here, the carbocation is involved. So I'll draw a nucleophile, carbocation. And this bond is forming, so that will be our partial bond in the transition state. Carbon goes from positive to neutral, so partial positive in the transition state, and then nucleophile is negative to neutral, so partial negative in the transition state. So each step with its own transition state. First one shows what happens first, which is the carbon to leaving group bond breaking. Second transition state shows what happens second, which is nucleophile to carbocation bond formation. Okay, so those are the transition states. Now let's do the reaction coordinate diagram. It is set up the same way as we saw for SN2, where we have energy, Gibbs free energy, relative energy, something like that on the y-axis, and then reaction progress. On the x-axis, we'll assume, I'll just leave a note here. Well, actually, I don't have to write it down, but we'll just assume it's endothermic. Okay, so we'll start with starting material somewhere, products somewhere off to the right. Now this will look different from SN2 because SN1 happens in 2 steps and we form this intermediate first, that carbocation. So somewhere in between starting material and product and higher energy than product is our intermediate, which is the carbocation. And we said that each step has its own transition state. So starting material to carbocation has a transition state, carbocation to product has a transition state. So we can write TS1 and TS2. You can use the transition state symbol either way. Now I drew TS1 at a higher energy than TS2. That was intentional. We said, just going to scroll back real quick. Step 1 is the rate determining step. That will be the slowest step. That's the step with the highest energy transition state, the largest activation energy. So we can show that this is the rate determining step going from starting material to intermediate. by having the higher activation energy and higher energy transition state. So we would say activation energy for the first step is starting material to TS1. And then activation energy for the second step is just intermediate to TS2. So much smaller activation energy there. All right, we will leave this for class, so we can work on an SN1 mechanism in class. I encourage you to try it before class, and then we'll go through it then. Next, we will talk about the stability of carbocations. So this is the intermediate in an SN1 reaction. It's also the intermediate in another reaction type we'll learn about in part 2 of Unit 4. The stability of the carbocation, well, we care about the stability of the carbocation because that's the high energy intermediate. If the intermediate is lower energy, then we'd be able to go from starting material to intermediate quicker. That would be a faster reaction. So we're learning now about factors that would lower the energy of the intermediate, the carbocation. So first, alkyl groups can share electron density that stabilizes the carbocation. This is referred to hyperconjugation. This is a really helpful way to predict whether something will be SN1 or SN2, is the substitution at the alpha carbon. So if the carbocation, well, let's remember we have carbon bonded to 3 groups. We're not going to specify what they are. And then the leaving group leaves, and we get the carbocation. Okay, so we're going to talk about how groups 1, 2, and 3, what I labeled there, if they're hydrogens or carbons or something else, how that stabilizes the overall molecule. So first, let's say it is a primary carbocation. So this would be a carbon, the carbocation, bonded to 2 hydrogens, and then in our group, so that's some carbon chain. This is the least stable. So only 2 hydrogens there. This would actually most likely go through SN2 reaction, not even SN1. Because it is a very unstable, we'll say least stable of what we're looking at. So it's very unlikely to form because it is very unstable. We are going to refer to carbocations by their substitution, so by the number of other carbons it's bonded to. This carbocation is bonded to 1 other carbon represented with that R group. So we call this a primary, or that 1 degree symbol. So we'll write primary which is a number 1 with a degree symbol. That's another way we can write primary carbocation. If we increase the substitution on the carbocation, we're going to get a slightly more stable. So we'll keep 1 hydrogen as a hydrogen. The other will replace, so if there are 2 carbons bonded to this carbocation, this is a secondary carbocation. This is more stable than primary, but still pretty unstable. Next, we have tertiary, which will be carbocation bonded to 3 R groups. Tertiary carbocation is pretty stable, and then what's even better is when one of these R groups is actually an atom with electrons. So I'll draw it in, and so let's say instead of a carbon, we have an oxygen. What can happen here is this oxygen can actually resonate electrons. So I'll draw the resonance structure here. Through that resonance, we now have a closed shell carbon. Oxygen is still closed shell. Even though it's positive, it still has 8 electrons in its valence shell. So this is the most stable version of a carbocation, is when it is stabilized by resonance. So this isn't called like a primary, secondary, tertiary. It is just a resonance stabilized. So with the most stable carbocations, that's resonance stabilized, these are more likely to go through SN1 reactions. But primary carbocations are very unlikely to form. And so those are more likely to actually not even form, because if you go through an SN2, you don't form a carbocation. The whole reaction happens in the same step. So you're never forming a open shell carbon. So if you are starting with a certain electrophile molecule and it would generate a primary carbocation, it will not generate a carbocation at all. Secondary is iffy. We'll come back to that later in this unit. It could kind of go either way. It depends on other factors. Tertiary is definitely likely to go through SN1, and resonance stabilized likely to go through SN1. So this is one important way to differentiate between SN1 and SN2 reaction pathways. Another factor that influences the reaction rate or the stability of carbocations is actually the solvent that these reactions happen in. So we haven't really talked about solvent much. But these reactions, when you're working in the lab and you're carrying out a reaction, usually everything is dissolved in a solvent. The solvent doesn't necessarily participate in the reaction. It could, and it does sometimes. But it is something that the reagents can dissolve in, and it'll help or hurt the reaction from moving forward, or it'll kind of be neutral. So remember, we're talking about this high energy intermediate, the carbocation. Carbocations, which are charged, are stabilized by protic solvents. So I have a list of protic solvents here. They are, well, if you look at what's similar across all of them, the hydrogens in each of these protic solvents are bonded to an electronegative atom. So each of these solvent molecules have polar bonds, resulting in partial positive and partial negative. And we could do that for the rest of these, where you have partial negative electronegative atoms, partial positive hydrogen. These types of solvents are best for stabilizing charged species. So let's write this down. like a carbocation. So for example, if we have water, it has the partial negative near oxygen and partial positive near hydrogen. So when a carbocation is generated, there is some attraction and stabilizing interaction because we have opposite charges here. Partial negative oxygen attracted to the positive carbon, and that's a stabilizing interaction. So we can write this out. So opposite charges being the positive carbocation and then partial negative oxygen. So protic solvents will help facilitate carbocation generation. Polar aprotic solvents, these are solvents that have polar bonds, so there is polarity in each of these molecules. Just a couple of examples of the polar bonds. But not as much of a electronegativity difference between the two atoms that are part of the polar bond, so it's not quite as polar. Protic solvents have a really large amount of charge, partial charges. Let me rephrase that. Protic solvents have more polar bonds than polar aprotic. So protic, the partial positive and partial negative are stronger partial positive and partial negative. In polar aprotic, they're weaker. So you can probably remember like dissolves like. Polar aprotic solvents are good for stabilizing polar uncharged molecules. An example would be like CH3Cl. We have a polar bond, polar molecule, but it's uncharged. This molecule won't create a carbocation. This is more likely to go through SN2. And the polar aprotic solvents also help facilitate that. We also have nonpolar solvents like petane, hexane, benzene, toluene. These are best for stabilizing nonpolar species. This all comes back to like dissolves like. Similar intermolecular forces are attracted to molecules with similar intermolecular forces are attracted to each other. So typically, SN2 reactions happen with polar aprotic. They're best with polar aprotic. They could happen in protic or nonpolar. But in polar aprotic solvents, we have Those are best for stabilizing polar uncharged molecules, which is kind of what we see in SN2. SN1 reactions are more likely to happen in protic solvents because protic solvents stabilize the carbocation intermediate and the negatively charged leaving group. SN1 reactions definitely won't happen in nonpolar solvents because they really won't dissolve in those solvents. Okay, let's talk about one more way that carbocations can be stabilized. This is through a carbocation rearrangement. That is a hydride shift or a methyl shift. So we'll talk about a hydride shift first. In our learning goals, this is listed as 1,2-R. That's a 1,2 rearrangement, and I'll show you why it's called that as we talk through it. So here we said this is hydride shift. I want to remind you all what a hydride is. Remember a hydrogen atom. So if you just draw the Lewis structure of a neutral hydrogen atom, it is, let's draw it over off to the right. So it'd be hydrogen with 1 electron. We have already talked about a proton. That's when hydrogen loses. So we're going to say minus 1 electron. We get H plus, and we call this a proton. If hydrogen gains 1 electron, now it has 2 electrons and it'll have a negative charge. This is hydride. So when we talk about a hydride shift, it is hydrogen shifting with 2 electrons. So if we assume this reaction goes through an SN1 reaction, we can write that. Assuming SN1, first the leaving group leaves, and then we generate the carbocation. All right, there's our carbocation right there. This is if we were in class, I'd ask you to tell me if this is a primary, secondary, tertiary, or carbocation stabilized by resonance. Well, the carbocation itself, so here's carbocation, it's bonded to 2 other carbons, so that makes it a secondary carbocation. Remember, this is not as stable as a tertiary or resonance stabilized. This particular reaction or this reagent could go through a hydride shift to generate a more stable carbocation. So from a adjacent carbon, this is why we call it 1,2-R. We'll say this is carbon 1, adjacent is number 2. And we are rearranging. We're going to take this, I'll highlight this hydrogen and shift it with its electrons to the carbocation. So this is a curved arrow, mechanism curved arrow from the hydrogen bond to the carbocation. So this generates a new carbocation right here because that just lost the hydrogen. And we have this new bond to a hydrogen. The carbon on the right is no longer a carbocation. This is the, didn't mean to do that. This is the hydrogen that shifted over. Now I'd ask you to reassess, is our carbocation primary, secondary, or tertiary? The carbocation that was generated is bonded to 3 other carbons, so it is a tertiary carbocation. Which, going back to when we talked about stability of carbocations, this is more stable. So this molecule, after generating the secondary carbocation, would go through this hydride shift so that a more stable carbocation can form. Very similarly, methyl shifts are possible. So again, we'll assume SN1. Oh. Okay, so first step will be losing the leaving group. And this molecule is a little different. That's intentional, so we can show the hydride shift. I'm sorry, the methyl shift this time. Okay, again, we've generated a secondary carbocation. This molecule could generate a more stable carbocation if it undergoes a methyl shift. So that is a CH3 and its electrons shifting over to where the carbocation is. Again, this is a 1-2 rearrangement to then form a more stable carbocation. So this, after the methyl shift with that mechanism arrow there, our new carbocation is this one. And then what was the carbocation is now bonded to 4 different things, so it's not a carbocation anymore. So the methyl that shifted over is now bonded to that carbon. The carbocation generated is bonded to 3 other carbons now, so it is a tertiary carbocation, which again, more stable. So I have this note here, this is really important. Hydride and methyl shifts only occur between direct neighbors. So that's why we call it the 1-2. It's not a 1-3. We can't keep going down the chain and shift over a hydride or a methyl. So only between direct neighbors. And then these shifts only occur if the resulting carbocation is more stable than the initial. They won't occur if you're going to if you start with the tertiary and then go to secondary, definitely not going to happen because that's not energetically favorable. Now there is usually some indication that a hydride or methyl shift may have occurred. This is an example. This says when starting material was added to H2O, this alcohol product was observed. Draw the curved arrow mechanism to explain this observation. So wherever the leaving group is, so this carbon, that's where the nucleophile bonds, but in this case it's at a different location. So that's one indication that a hydride or methyl shift may have occurred. Another way this could be indicated is if you are given information about the reaction coordinate diagram, because this requires an additional step. We expect SN1 reactions to go through 2 steps, but if it goes through 3, maybe it's a hydride or methyl shift as that 3rd extra step. I'll also emphasize that in the methyl shift molecule, so let's focus on this molecule. When we had this carbocation, a hydride shift is not possible, or wouldn't generate a more stable carbocation. This carbon bonded to carbon 1 doesn't have a hydride to shift over. This one technically has a hydrogen, but if you shift that hydrogen to this carbocation, this carbon becomes the carbocation, and that would be a primary carbocation, and that is not as stable. For the first molecule, so going back up here to the hydride shift, with this carbon being the carbocation, A methyl shift is not helpful because we started as secondary. If we shift this methyl over, we would end with another secondary carbocation. So if you're stuck, you could test out different possibilities and double check that whichever one you end with actually does help stabilize the carbocation with that shift, a hydride or methyl shift. I want to make sure we have time to talk about these types of things in class, so I will save this example. You can try these practice questions, and then this is the end of the part 1 notes. And so we'll have time to review some of this in class. If you have questions, I encourage you to write them down so that you remember when you come to class what you want to ask about. Maybe try out these learning checks, and I will see you in class.